Anybody knows what is builder? Piece of software. Hi, can you hear me online?
Yes, sir.
Yes, sir.
Okay. Okay, so we'll start. Okay. So before we start, just wanted to mention that yesterday I talked to Subodh sir about how we are planning to continue this activity. So this week and next Sunday we'll have lectures, and after that for a few weeks we'll take a break because some of you will have INMO exam to write, and you're also maybe busy with your final year school exams and things like that. So how to continue after that we have to plan. So for now, this lecture and the next lecture will be the last ones that we plan. And I'll give you some ideas that what you can continue to do until the next year's training starts. Okay, so that was one quick thing I wanted to share. And so actually that really matches our schedule well because I mean we are doing geometry transformations. I think we'll be done with the topic pretty much today and by next lecture. So that will be a good conclusion to whatever we are doing so far. Okay. So for those who are not there last time, I just started to talk about spiral homothety. We took some examples of that. But before that, I think that completes the big picture of the important transformation that we need to study. Okay, so just want to frame all of them in one context that what are all the transformations we have studied so far. And today we are going to start looking more closely at the relation between them and complex numbers that we have been mentioning that once in a while, but we have not really completely used complex numbers as a tool that how you can solve problems with complex numbers. So that is something we'll see some applications of that today. Okay, but just to again start with the, I mean, we have written this table a few times, but it's always good to revisit this table of all the transformations. Okay. But before that, just a side note, I mean, because we are going to rely on complex numbers, let me just recap and make sure everybody is now comfortable with this basic understanding that any point in the plane, right? If there is any point with in real coordinate it has xy coordinates, then we also know that we can also express the point in polar coordinates, right? So like r angle theta is how sometimes it is written. So the distance from the origin and the angle it makes with the positive x-axis. And in the same way, the same point can be represented by a complex number, which is typically denoted by small p. And so that complex number, the value will be x plus iy. So x is the real part, y is the imaginary part. And we can also write this as r times cos theta plus I sin theta. Okay. Or we abbreviate that as r cis theta. So these three, four ways are describing the same object. So we should all be comfortable with that, that there is a point, the geometric concept of a point or a ordered pair of real numbers or the same ordered pair expressed in polar coordinates or as a complex number, again expressed as x plus I real and imaginary part or as r and theta. So these are 4 or 5 different ways of writing the same thing. And sometimes one interpretation is more helpful than the other as we have seen. So yeah, that is basically what we need to know for sure. So then, like, what are the transformations that we have seen so far? So the first is, of course, translation. So translation requires us to denote what is the vector that we are applying. So if I say that translation by vector a plus ib, right? Or this is the x and y offset that you want to apply. Then any starting point p, right? If it has coordinate x comma y, or in complex number, if I write it as x plus iy, then under this operation, the new position will be x plus a plus I times y plus b, right? It is just going to add the x and y components. Then we have seen rotation. So rotation around origin for now. So when we are rotating around the origin, so we need to know the angle theta, right? The angle of rotation is what we need. And so if we know that angle and if we know the coordinate of any point P, so in this case it is easier to express in the r and theta. So instead of writing it as x comma y, I could also write it. I don't know. What? Did I do something? If I express it as the angle and the distance, then it is easier to write, right? Then what will be the result of this operation? That rotating around origin. Okay, I don't call both of them theta. Let me call this alpha then. Okay, so if I'm rotating my angle alpha, then the new position will be the distance from the origin will not change, but the angle will be theta plus alpha, right? So that is rotation around origin. Then we also saw reflection in x-axis, and that doesn't require any parameters because we already said that we are reflecting in x-axis. So there simply the point x comma y, which we if we denote as x plus iy, then or if I denote it as z, then that becomes x minus iy, which we call z bar, the conjugate of z. And then homothety. So again, homothety around origin. So for that, we need to specify some real number k, which will be the ratio of homothety, that how much you are going to dilate. And so here actually you can either use the normal coordinate system or the polar coordinate. In both, you can express it pretty well, right? Because in the if I express p as x comma y, so that is x plus iy, then what will be the new position of the point after the homothety around origin? Kx plus ky, right? It will go k times far away from the origin. It will be kx plus I times ky. Or if I want to express the same as angle and distance, then that will be kr angle alpha, right? Right. The angle from the origin does not change, just the distance is going to be k times far away. And here k can be positive, negative, you see in all those cases. Like when k is negative, it's like an inversion through the magnifying glass, that the image becomes reverse. But the orientation does not change importantly. Like anti-clockwise remains anti-clockwise. It's just the visually it looks rotated by 180 degrees. And then finally we looked at uh, spiral homothety. So actually spiral homothety is nothing but a combination of rotation plus homothety. So whether or not you want to call it a separate operation, it is useful to think of it as a separate operation because it is very useful. That is why people created this concept of spiral homothety. Again, let us say around origin. Okay. And so for this, you need the ratio as well as some angle, right? So how much is the dilation and how much is the rotation? And when you combine both of these two, you get the spiral homothety. So again, it is easier to write this in uh, polar coordinates. So if r angle theta is the original point, then after this, so the distance will be k times far away and the angle will be added, right? Okay. So this is what we have studied so far. Important to mention that this operation, right? If you look at this operation, in particular, let us look at spiral homothety. The going from this complex number to this complex number can also be thought as a multiplication in the complex domain, right? Because if you remember how we defined multiplication of two complex numbers, and we derived that when you multiply complex numbers, their magnitude gets multiplied and angle gets added. So you see that applying this spiral homothety of k and alpha is the same as if the call the original complex number as z, right? Then you see that the new complex number is simply z times the complex number defined by k angle alpha. Okay, so if you have a complex number of magnitude k and angle alpha, and you multiply that complex number with the original point, you are going to get the same result. Okay, so this is one important interpretation of spiral homothety, which maybe we did not talk about last time. And another way of describing the same thing is that uh, one way to all of this, like rotation, homothety, spiral homothety, for all three of them, like rotation, homothety. Firstly, I think we can see that this rotation and homothety are just special cases of spiral homothety, right? If you said the angle alpha is zero, then it is just homothety. Or if they said the ratio k as one, then it is simply rotation. So actual spiral homothety is the most general case. So one statement which is applicable to all of this is that basically what this transformation does to any point. So what does to so the special point which has coordinate 1 comma 0, you just observe what is happening to that point, and whatever happens to that point happens to every point in the plane. Okay, let me explain what that means. So basically, if you think about it, right, what if the diagram looks something like this, that so this is our origin and this is our that special point 1 comma 0. Okay, and let us say we are talking about the operation is spiral homothety with a ratio of k is equal to 2 and angle is 30 degrees, let us say. Okay, so we are going to rotate by 30 degrees and dilate by 2. So under this operation, I'm let us say there is some different point over here, and I want to know that what happens to this point. So let me take the point slightly different location. So what happens to this point? I want to know. So the way I think about it is that let us apply this operation to the point u. Okay. So under first, if I let us say I do the dilation, so the point u will go from 1 comma 0 to some 2 comma 0 over here. And after that, when I do the rotation by 30 degrees, it will land somewhere over here. So somewhere over here. So if I call this new position u2, right? So u became u2 under this operation, right? And so what is the characteristic of u2? This angle is 30 degrees and this distance will be 2. So if you want, you can find the xy coordinate also for this. So the remarkable thing is that if you look at the shape of this triangle and if you just copy that shape on this line OP, you will get the resulting position of the point P. So let me consider triangle OUU2 and let me construct a similar triangle OPP2 with the same correspondence over here. So OP. Then do you see that P2 will be the image of P under the same operation because of all the similarity and everything, right? Because basically what will happen, the ratio OP2 upon OP, because by construction, let me write it in the right order. So by construction, these two triangles are similar. Triangle OUU2 is similar to triangle OPP2. Okay. As a result of that, what is happening is that the ratio, if you look at the ratio OP2 upon OP, is the same as OU2 upon OU, and that is that constant K, which we in this case is 2, but the number does not matter. And similarly for the angle, that the angle formed by P2OP will be equal to angle U2OU, and that is equal to alpha. So in this image, actually I should use a different color. So in this image, this angle will be equal to this angle, which is alpha in general. And if this original distance was r, then this distance will be k times r. Okay. And for this, like if you take special cases, like here K and alpha are both non-trivial, but just if you imagine in this situation that let us say K is 1, so we are talking about purely rotation, then even P will get purely rotated, but you will get two similar triangles, right? So that OU U2 and OPP2 will always remain similar. Okay. And again, to highlight the fact that this is a multiplication operation, can you think of reaching the point P2 in two different ways? In this diagram, if I start from the point U, okay, so from point U, which has coordinate 1 comma 0, or in complex number, if I have to write a complex number of this, it is simply 1, right? It is unity, right? If I denote it by small u, it is unity. Okay. So I have two approaches to reach the point P2. First approach is from U I reach U2 first. No, sorry. From U I reach P first. Okay. So let us say reach point P, right? And so let me give some coordinates to this point P. I mean, we denote it by small p obviously, right? So to reach capital point P, I can say multiply by P, right? So the original coordinate U, if I multiply by the small p, I'll reach the point P. And after that, if I multiply by this U2, right, this vector K alpha, right? So then from there to reach P2, I have to multiply by let me call it Q temporarily. So the coordinate of this point is Q, which has magnitude K and angle alpha. So basically, this point is nothing but 1, which is trivial 1 into P into Q, right? The starting position was 1, to which you first multiplied P and then you multiplied Q. But we know that multiplication is commutative. So couldn't I reach the same point by first multiplying Q then P? So in that process, if I this is one journey, like if I write this as one journey, I could do the same process again starting from 1. But this time I'm going to multiply Q. So basically from here I'm going to reach here first, right? So I'll first reach U2, which has coordinate Q. And then from U2 I need to go to P2. So what will happen? To go from U2 to P2, what is the operation I need to perform? Sorry, operation. Okay, so to go from U2 to P2, right? Do you see that there is one more triangle which is similar to OU to P2? Which triangle is similar to OU to P2?
OUP.
OUP, correct? Do you see that? So that line segment which I highlighted can be compared to this line segment, right? So this triangle is similar to this triangle. And so that is the reason why going from U2 to P2 is a multiplication by P, because again the principle is what the transform does to the U, it does to the whole plane. So the going from U to P is a multiplication by P. Therefore, going from U2 to P2 is also multiplication by P. So it highlights the fact that you can reach this P2 from two different ways. And in both cases, you are just applying two spiral homotheties in different order. Okay. But yeah, anyway, I mean, this is all just to improve your way to visualize what is a transformation, what it does exactly. I think it would be very good that if you start to think of transformation not as a operation on individual points, but on the whole plane itself. Like you have seen your graph paper, right? So imagine that the whole graph paper is getting stretched and rotated. It is not like one point at a time it is doing. The whole plane is getting transformed in one go. So in that process, of course, you will go two times far away, P will go two times far away, and everything gets rotated. So it is like you need to imagine that kind of a global operation. Okay. So now coming to some applications of this. So we started to look at MyQuell's configuration last time. So I just want to revisit that because I didn't realize we are doing it in the wrong order. I mean, actually, Mikkel's theorem starts from the end point of our analysis last time. So what we started was we started with the most difficult theorem and then we proved the easy theorem. Let me do it the right way. So Mikkel's theorem, what it originally says is that if you have any triangle, okay, and if you take any points on the sides of the triangle, right? So let D F be any point. Then what Mikkel's theorem originally says is that if you draw those three circumcircles, they are concurrent, right? So this then circles, like basically you take one vertex and two points on the sides. So circle A, F, E, B, D, F, and C, E, D. Okay. So no matter which 3 points you take on the sides of your triangle, what this Michael's theorem says is that they are guaranteed to be concurrent at a point. Okay. And this is pretty much easy to prove because basically what you get cyclic quadrilaterals, right? Like if you assume the meeting point of two of them as this point P, right? So if like let two circles meet at P, then by chasing the angles, you can easily show that it also on the third one. Because if I just join let me delete the circles temporarily. Just denote the point over here. Like assuming that P lies on two circles, then what will happen is if I call this angle alpha, then the same alpha angle is here also and here also. And so therefore, actually this color is very hard to read. Right? So therefore, if P lies on any two circles, it has to lie on the third circle. So this is the basic Mikkel's theorem, but basically what we observed last time is something more about the point P. That point P is not just any arbitrary point. It has an important property that the position of the point P only depends on the shape of triangle DEF. This is the important addition, which typically is not part of standard Mikkel's theorem, but it is studied as an extension of that. That if I change the position of points DEF, in general, the point P will also change. But if the shape of the triangle DEF does not change, then P will also not change. That is the important point. Okay, and we had already seen the proof of this last time, so I won't repeat it. Okay. Just to mention one more proof, because last time we had done it using transformations, there is one more way of kind of proving the same thing, which is that in the diagram, if I just chase a few angles, right, you get the same thing. Like if I just, let us say that we have proved the concurrency, so we have all these cyclic quadrilaterals. Now, if you just look at, let me just mark some angles. So let us say I call this angle alpha and beta. So given that the shape of DF does not change, so the alpha plus beta does not change, right? So alpha plus beta in this diagram remain constant. And if you just change the cyclic quadrilaterals, where this is going to go, this alpha will be here and beta will be here. Right? So wherever the point P lies, if we know the shape of triangle DEF, we know alpha plus beta. Okay, and if you just look at the angles at point B and C, I can know the complement also, right? So if I call these angles gamma and delta, then I can compute gamma plus delta as simply B plus C minus alpha plus beta. So that is also going to be constant. And so now the simple question is, if I have 2 points B and C like this, right? And if I have any 2 points B and C, and I look at the locus of all the points P such that this gamma plus delta is constant. So gamma plus delta constant will give me some locus of that point P. In general, I think it's a complicated shape. I don't think it's a simple shape. What is the shape of this? Whatever, it basically it is some curve, right? So basically, P has to lie on that particular locus of all points for which gamma plus delta is constant. And the same thing you can do from all three sides, right? So you are going to get three loci for the point P, one from each side. That just as gamma plus delta is constant from side CA, some beta plus some other angle will be constant, and so on, right? So
Excuse me, sir.
yes,
So if gamma plus delta is constant, that angle BPC must also be constant, right?
BDC, why?
BPC.
BPC is constant. Yes, correct, correct, correct.
Then it will be a circle, right?
Oh, oh, sorry. First key. Then I was imagining something else. Yes, correct. Obvious. What you're saying is correct. Gamma plus delta is constant, so it is just going to be a circle. I thought it's going to be some parable or something. So yeah, then it's simply a circle where we know the arc. So BPC will be a circle, correct? And in the same way, I'll get one more circle from CA and AB, right? And where all those three circles meet, the point P will have to be there. And even if your triangle DF changes, this gamma plus delta does not change. So that is the reason why the point P has to be the intersection of all three circles. So in fact, what this means is that you can locate the point P even without drawing triangle DEF inside the triangle. Like if I were to give you this task that locate this point P, in fact, we had this question, right? We want to construct an equilateral triangle whose all three vertices are on the sides ABC. So what I'm showing you is there can be a proof to do that without constructing the triangle directly. Like for example, suppose like if you just chase that possibility for a minute, like I'm interested in an equilateral triangle getting formed over here. So corresponding to that, whatever the point P, I want to locate that point P. So I can sort of reverse chase it in this way that joining these points, I know this angle alpha and beta, right? I mean, I don't know the values, but I know alpha plus beta has to be 60 degrees. Therefore, if I join it this way, then that alpha and beta are going to come out here. And if I call this angle gamma and delta, then what I know is gamma plus delta has to be equal to B plus C. So where ABC are my original triangle minus alpha plus beta, which is 60, right? So therefore, angle BPC will be its supplement, right? Will be simply 180 minus B minus C plus 60. So that is simply 60 plus 8, right? So in other words, if I draw an arc of angle 60 plus A on side BC and same on CA and AB, wherever they meet, that will be my point P. I would like to do this construction actually. So if I take any triangle ABC and inside that I'm interested in constructing equilateral triangles. So I just have to, on side BC, I need to construct an arc of angle 60 plus A, which means the central angle has to be 120 plus 2A, or the complement of that has to be 120 minus A. So where the center of this circle will be BPC 60 plus A. So this angle is 120 plus 2A. This angle is 360 minus this. So that is 240 minus 2A. So each side will be 120 minus A. So this will be 90 minus this. So A plus 30. So if I consider an isosceles triangle where the base angle are A plus 30, then that will give me the center of the arc which I want. Sorry, A minus 30. Okay. And so depending on whether A is greater or less than 30, the point may come above or below the line. I think in my diagram, hopefully it will always be minus. काय केलं त्याने नाही clockwise केलं का? मायनस तर मायनस का केलं त्याने? So this is the one line. Let me just intersect with the angle bisector, perpendicular bisector. And similarly on the other side. Why is it rotating counterclockwise when I say clockwise? I think. Okay, so wherever these two circles meet, it doesn't look like it has done the right thing. I don't know. It doesn't look like the right point. If नक्की A minus 30 है ना? BPC is 60 plus A. So BO1C was twice of that, 120 plus 2A. So the Atla BOC was 240 minus 2A, so 120 minus A. So 90 minus. बरोबर आहे. And we'll check. I think चूक केले मी because that doesn't look correct in the diagram. Either the construction is wrong or the derivation is wrong. Something is wrong. But anyway, I mean, this was just wanted to check if we can quickly show this. But you see in principle that we can do this, and not just for equilateral triangle. For any triangle, we can find the point B directly through the arcs. Okay. But now we are going to see how to apply this to solve one more problem, like the construction problem which I had given some time ago. Maybe I'll give you a chance to try it again. So if you remember, we had done 3-4 construction problem. One is that we just want an equilateral triangle whose one vertex is fixed and two vertices are on two different lines. Then there was a question where I want an equilateral triangle whose all three vertices are on the side of a given triangle. But out of all those infinite ones, I want the smallest one. And then the fourth question is, why don't we extend this for quadrilaterals? So think about this question that given a quadrilateral ABCD, construct with ruler and compass. Okay, I say technically inside, but maybe the point can go outside the segment also. But the point is that each vertex of PQRS has to be on one side of ABCD. So the diagram will look something like this. If this is your quadrilateral, then I'm interested in drawing a square which looks maybe like this. So in the case of equilateral triangle inside any arbitrary triangle, we found infinite solutions because we could choose any point we want and we could get it here. But here, most likely, it is not going to be like that. It will be a unique. So the question is, uh, like, is there going to be always one solution, and is there going to be more than one solution? So both questions are interesting. And there is a very famous conjecture which I'll talk about later on. There is an unsolved problem around this one, which goes into the category of those, $1 million questions. If you solve that, you get $1 million. Okay. So just as a refresher of what the problems we have solved so far of a similar type and why that technique may or may not work here. So going back to the very basic problem we solved was that if you have only two lines and a point given, then how do we construct the equilateral triangle? So there what we did, we rotated one line by 60 degrees, let it intersect the other line at some point. So if I rotate line L1 by 60 degrees, let it meet here at some, so L1 dash is the rotation, and wherever it meets, we said that let that point be the point Q. And so that Q has to be the image of some point on the previous line, and therefore we can complete that equilateral triangle. And when we moved from that to a triangle case, like inside a triangle, what we were doing, again, if the question is just construct any equilateral triangle, then there are infinitely many solutions because this point P I can choose anywhere on the side AC. But then if we were asking that we want the triangle with the smallest area or smallest size, anyhow you define it. So then in that case, we have to, what we can do is repeat that process for any point over here. So we'll get what triangle PQR, right? But more importantly, we'll get that point of concurrency. Okay, we cannot call it P again. Let me give it some other name K. Okay, so the K is the point of that Mikhail theorem concurrency. And so the observation was that K will be the same point for all the equilateral triangles. And actually, one important thing which kind of got missed above, let me just go back to the part above, because there is a very important point property of the point P, that when we say that the position of the P only depends on the shape of triangle DEF, along with that, uh, what I want to say is that the relative position of P inside DEF is also constant. Okay? What does that mean? You know, let me add that. And so the relative position of P what does this mean? See, the position of P is of course fixed. Even if triangle DEF changes, P does not change. But what I'm saying is that with respect to triangle DEF, that for triangle DEF, whatever angles the point P makes with the three sides, those will also not change, right? So if I join the point P to the three vertices of DEF, right? So this alpha, beta, like whatever, if I mark similar angles on all the sides, those angles will also not change. Like in the, if I separately draw triangle DEF as a reference, right? In triangle DEF, if I want to locate the corresponding point P, right? If I copy the same angles, if I copy the same angle alpha, beta, and all the other angles, then whatever point I get, that point will always remain the same, even if my triangle DEF changes. So if somebody takes a different triangle D2, E2, F2, so the triangle D2, E2, F2 has changed. Although point P has not changed, these angles have not changed. So if I join this, like for example, like this, then if this was beta, this will also be beta. So that is what I mean by the relative position. I mean, you can think of it like every point in the plane has an additional coordinate system defined by how much angles it makes with a given reference triangle. Okay. If you think about it, like if I choose any triangle in the plane, sorry, this is becoming a bit of a diversion, but this is an important point that if I choose any triangle in the plane, right, then I have an additional coordinate system where if I pick any other point in the whole plane, then I can ask the question that what are the angles that it makes with the three sides? Like if I just call this angle alpha, beta, gamma, then this triplet of values alpha, beta, gamma uniquely defines that point in the whole plane, right? If you change alpha, beta, gamma, the position of that point will change. Under this system, for any triangle DEF you pick, relative to that triangle, the coordinates of this point P are going to be the same. And so realistically, what it means is that if the point P is, let us say, the orthocenter of DEF, it will always be the orthocenter of DEF. For the entire family of those DEF similar triangles, P is the orthocenter for all of them. Or if let us say P is the centroid, it is going to be the centroid for all of them, and so on and so forth. So that is what I mean by the relative position does not change. Okay? I don't know how to express this concept in a different way, but I hope you get this idea of angles formed from the three vertices. So in that sense, going back to this question, so there, when we wanted to find the equilateral triangle with the smallest size, we know that the relative position of K does not change. Therefore, we can use K as the center of spiral homothety. And if I just draw perpendiculars from K to the three sides, right, then those feet of those perpendiculars are going to be my smallest equilateral triangle. And the reason for that being that in any, if I just draw that triangle PQR separately over here, okay. So let us say PQR is my triangle, and as we already noted that the position of K does not change, which means if I think of this as a similar triangle, then the ratio PQ upon KP, right? So the ratio of K, the side of the triangle PQ upon K, PK, right? That is also does not change. So if I want to minimize PQ, I should minimize PK, right? So therefore, the only way to minimize PK is I should choose the point P, which is the foot of the altitude. So that is why that construction works. Actually, we did not fully appreciate this point last time when we did the problem. That the reason why this construction works is that this ratio does not change, and therefore we should pick the smallest denominator for the smallest numerator, or vice versa. So all that is fine. But now coming to the question we want to solve, because now we are not talking about a triangle inside a triangle, we are talking about quadrilateral inside another quadrilateral. So what can go wrong? That what is the issue with, why can't we just apply what we learned over there over here also? Like for example, if somebody says that, let us say triangle, so ABCD is a quadrilateral, and I want to construct my square. So like somebody could say, let me just pick any point on this side, okay? So I'm interested in PQR. So let us say this is my point R. Okay. So I expect P somewhere over here, Q over here, and S over here. And I want a square like that. So the first question is, can you construct the square where I need four conditions to be met, right? P has to be on the first side, Q on the second side, R on the third side, which is already given because I'm choosing R over there, and S is on the fourth side. So maybe satisfying all four conditions at the same time is a very big task. Can we do it step by step? Like first, can we construct a square where three of the conditions are met? Forget the point S. I just want PQR on three given sides. Can that be achieved? Yes. Because it's the same the equilateral triangle trick only, right? Because what is the key idea that the shape of the triangle PQR we know it is a 45, 45, 90 triangle. So, like if I just draw it somewhere over here, let us say this is the square. And again, that point S is not on the fourth side, but for now, let us say I don't care about that. Okay. So if the shape of this triangle is fixed, right? We know it is a 45, 45, 90 triangle. Then in terms of geometric transformation, see the reason why this first operation works, right? That because we know that the point Q is related to R with the 60-degree rotation. In the same way, how will you relate point Q and P this time with respect to some transformation? What is the transformation that will take point P to point Q, for example? See, in the case of equilateral triangle, it was just one rotation, right? See, the fixed point P has to be used because that is the only thing we know. So we have to use P as the center of the operation here. This time the fixed point is R. So I have to use R as the center of my operation. Then what is the operation to go from P to Q? Correct. Correct. Right? It's a spiral homothety because if I just rotate, then point P will not go to Q because the distances are different. But some combination of rotation and dilation will work, right? So the angle of rotation is 45 degrees and the distance will be reduced by 1 by root 2, right? So if I say that, so if I have to write it properly, I can say Q is the image of P and the spiral. So spiral homothety requires four inputs, no, three inputs. First is what is the center of homothety, which is R. Then how much is the angle? And I should say clockwise, anti-clockwise. Let us say I just use signs to convey that information. Positive is anti-clockwise. And ratio will be 1 upon root 2, right? Because of 45, 45, 90. So if I apply this operation to the point P, right? Then that will go to the point Q. And again, if you know directly think of paramobility is one big jump, you can always break it down into rotation plus dilation, right? So let us say you first rotate the point P and then you dilate it. Same thing. So can we apply the same trick for that? What we did for the equilateral triangle case, we did not know the position of point P, but we know the whole line, right? We know the locus of the point P. So why don't we transform the whole locus in that way? So if I take this entire line AB and apply the same spiral homothety, won't I get a line passing through the point Q, right? So therefore, if L is my original line, so L is the line AB, and L dash is the transformation of uh, the same spiral homothety. L with the same parameters. So parameters mean everything is the same. So under the same spiral homothety, L will become some line L dash. And wherever L dash intersects my third side, the BC, right? So L dash intersection of the BC will have to be the point Q. So that is how I can obtain point Q, and once I obtain point Q, I can complete the square, right? So in this way, I can ensure that three of my conditions are met, that the point P is on one side, Q is on second side, R I have chosen to be on the third side anyway. And if we are lucky, then the point S will lie on the fourth side directly. But in general, we are not going to be lucky. So one option is I can keep changing the position of R. See, for every point R, I'm going to get this unique square. So if I just keep by trial and error, I can keep changing the position of R. Every time I get a different position of S. So that is the question, that do we need to keep doing this trial and error, or is there a smarter way? Extra pen है? You have a pen? नहीं नहीं, you keep it. I'll take one. Extra pen क्या pencil असेल तर. Yes, anybody has a solution? So as of now, the best strategy we have is trial and error, right? We can keep changing the position of R every time we get a new point S, and once in a while, like probabilistically, there is a 0% chance that we'll get it right because there is only one unique position and infinitely many wrong positions. But let us try it out. Like, let us see what happens. So I'm just going to. So ABCD is my any quadrilateral. Okay. So I choose some point E as my starting point, and now with E, I'm going to apply this process. So what I need to do, I need to rotate and dilate the line AB with that 45-degree and what 1 by root 2 ratio to meet with line BC. So let me start by first drawing the perpendicular on that line. So in order to transform that line, I'm just going to transform the point F and then I'll draw a perpendicular, right? So I'll first bring EF. Let us say I first rotate it by 45 degrees. So correct. So if I just rotation, then if I drop a perpendicular EF dash like this, that will be the rotated line. But now I need to dilate it also. So let me also dilate it. Now how do I enter 1 upon root 2? I hope I can enter that. 1 upon this one. No, we can do it. No, yes. Okay, so it became F double dash. So if through F double dash I draw the line which I want, perpendicular line. So where this line is meeting my second side. So this is my second vertex of this square which I want, EG, right? So if I just directly construct the square, I have a square tool. I should choose E, then G. So I constructed the square and you see how nicely the third point is landing on my third side. But this point H, which was that S, is not on our fourth side, unfortunately. Right? But, and so, I mean, what you could do is I could change the position of the point E and you'll get a different position of the point H. So what is your conjecture about the point H?
As changes, H will allow in that.
So Ruhan has a conjecture that when I change the position of point E, H will move on some line. And if that is true, then can we solve our question? Because I can maybe choose two positions of point E, and wherever that line intersects my AD, that will be my point S, right? And so let us see if that actually happens. So let me enable tracing for this. So as I move point E, look at that. So H is moving nicely on a straight line. So therefore, it looks like this could be one way to solve the question, but of course we have to answer why is it on the straight line. Okay. To motivate that answer, that why is it a straight line, let me just rearrange the diagram a little bit because I want to. We are studying this property for a long time, this configuration, but just we are not familiar with it. That is why it is looking a little bit strange. But let me just make it look little bit more familiar. Then maybe you can see the connection. Okay. So what we have been doing And note that actually to construct this square, what we really constructed was this 45, 45, 90 triangle. That fourth point is an added bonus, but we never wanted that fourth point directly. So if you think about it, what is invariant in this diagram? Like if I give this point a name, right? The intersection of these two sides of my triangles. Like this is my original quadrilateral ABCD. So let AB and CD meet at this point J. And look at this triangle CBJ. And inside this triangle CBJ, what can you say? As per construction, what have we really constructed? So don't you see that actually what we constructed is this 45, 45, 90 triangle, right? EIG, whose shape is not changing. So isn't this Mikkel's theorem kind of configuration? That I have a triangle of a fixed shape where three points lie on three sides. And so based on that and what are properties you have studied so far, we should be able to prove why H also lies on a straight line. Okay. But again, I'll give you some time to think that how you are going to put this together with the Mikkel's theorem properties to finish this problem. But I hope you realize something important, that how we are looking at this problem, that if you take a quadrilateral and you ignore one side, it becomes a triangle. It is like, okay, serial, सास भी कभी बहू थी. So every quadrilateral has many triangles in that. And I mean, that is a very important, I can imagine so many questions can be asked around this concept. That the realization that in a quadrilateral, you can also apply properties of many triangles. Yeah. What happened? You got it?
I got it.
Okay. So this diagram looks like Michael's configuration, but so how should that help us? That what aspect of Michael's configuration could be useful here? That what we have studied is that when you have a family of triangles inscribed like this, where all of them have the same shape, what all happens to these triangles? Mhm.
If this point M is the point of concurrency,
Yes,
then this ratio should be same.
correct.
Sorry.
No, you're on the right track. Basically, the position of the point S, like basically think of triangle PQR as a frame of reference. In that frame of reference, the position of S is always fixed. So even if your frame of reference changes, if it was originally a square, it will always remain a square, right? Something like that. Let's see how we can articulate that in the right way. So the important addition in this diagram is that point of concurrency, right? That we have not added in this diagram so far. Let me go back to the drawing board. Uh, so what you're observing so far is that we have a larger triangle. In fact, let me not even draw the fourth side of my quadrilateral. For now, it is not really important. What is given or what we are focusing on is that on this triangle, there are points on the three sides which form a 45, 45, 90 triangle. Again, actually, the that detail is not important. It could be any shape. There is nothing special about 45, 45, 90. It could be any shape as long as it is a fixed shape. And what we have constructed is that this PQR shape does not change. And so based on Michael's theorems, uh, and let me just change the notation for now. I know we are talking about ABCD different points, but in this diagram we are comfortable with that. So here, as the PQR triangle changes, like without changing the shape, what we already observed is that that point of concurrency, if I call it K, that does not change, right? That is the point where all those three circles pass. And the relative position of K does not change. That is the thing I want all of us to focus on. So what is the relative position? That all the angles that K forms with the inner triangle, right? All of these angles are fixed. So now let us say complete that square. So if I complete the square PQRS, do you see that if PQR is with respect to PQR, K is not changing, then S and K will also have the same relation. Like whatever angles that we are going to write here, like you can give any names. You call this angle alpha, beta. Every angle in the whole diagram is always going to remain constant. So K is remaining fixed. These angles are remaining fixed. Like just to give it some name, like for example, can I say that S is the image of R under spiral homothety around K, which what I'm saying is that the shape of this triangle, right? SKR, let us look at this triangle SKR. The shape of that triangle is fixed because all the angles are fixed. So I know exactly what is the operation of homothety around point K, which will allow me to go from R to S. That I need to rotate by this angle and I'll need to scale with that ratio of those two sides. And so if R is moving on a straight line and you apply some fixed homothety transformation to that, won't its image also be a straight line? So therefore S has to move on a straight line. And again, in this, we are not making any special reference to it being a square or 45, 45, 90 triangle. So you see, it could be any shape. If I give you that, construct a quadrilateral of this shape inside ABCD, you can do that. It could be, doesn't have to be a square. So for this kind of question, I really feel that GeoGebra is a very powerful tool because visualizing how the whole framework is rotating, but still relative to each other, the components are in the same place. That intuition is very important. Then everything, the calculations are not that important. This intuition is the important thing. Like if you go back to this diagram, let me plot that point of concurrency. We have not drawn that here in the diagram. If I just draw the circumcircles of three of these, right? Like I want you to appreciate that constancy, that what is not changing is very important. So if I just construct the circumcircle of these two, so this point, I won't draw the third circle because the point will be the same. So this point, or they call it K. So K is the point around which everything is not changing, rather, I would say. So if I measure any angle, any ratio in this quadrilateral with K, like if I just randomly look at angle EKH, right? So if I look at angle EKH, right, it is some 60.8 degrees. Okay. And so what we want to focus is on the fact that as the point E changes on this line, so K is remaining fixed and the relative position of H and E with respect to K is also remaining fixed. That is why like the whole world is rotating around the point K, you can say. Everything about this triangle square will rotate around the point K. So you see, so in this diagram, I think we're very clear what I mean by the relative position. You see where K is inside this blue square here. And if I change the position of point E, with respect to blue square, the K looks at the same position, like distances from the side and everything. No matter how small or large I make the square, for that square, the position of K has not changed at all. So that is what we mean by relative position. Okay. So like if K was some special point like midpoint of one side, it will always be the midpoint of that side, and so on. Okay, so is this clear that so how we are able to finish this construction problem now that you could so three ways that you can either construct this point K and from there you get it, or you just take two random points R1 and R2 and use that to finish the problem. Okay, as a homework, I would also like you to prove this with pure geometry. It is possible. Actually, it's a good exercise that even if without using transformation logic, you can prove this statement. Okay, so prove that. And for now, let us do it for a square. So consider a fixed quadrilateral ABCD. Let's pick it. Oh, yes. So try to prove this with pure geometry. And what we're doing is also pure geometry, but even more pure geometry. Right? If 3 points of the square move on three lines, then the fourth point also has to move on a fourth line. Like basic proportionality theorem and those kinds of things are also enough to prove this statement. Okay, so then I want to switch to a different question. This is like a very proper geometric question. So far we have been doing lots of construction problems, but even where we have to prove something, how transformations and complex numbers. Now this time the focus is on complex numbers. That how complex numbers, the interpretation of complex numbers can help us to solve a problem. So let me just write the question. And please let me know in case you already know this question. So given any quadrilaterals A, B, C, D such that so there is a square any quadrilateral whose diagonals are equal in length and perpendicular to each other. Now construct Okay, so if you construct squares on all four sides of your quadrilateral and take the centers of those squares, those centers also have the same relation that they are equal and perpendicular. Anybody who already knows this question? Anybody online?
Yes, I've seen once.
Okay. So have you solved it with complex numbers and those kind of thing or any other approach?
No, pure geometry.
Pure geometry. Okay. Actually, I have not solved pure geometry. So I'll suggest you can also try pure geometry approach, but do that as a homework for now because I want to show you the complex numbers or transformation way of doing it. So try to think in that direction for now. Oh, I'm sorry. I remember the question wrong. Sorry to. So, Om, did you solve the same question? Remember if you solved the same question?
Like I think condition AC is equal to BD and AC perpendicular to BD not needed.
Is it
Yeah.
true for any quadrilateral, right?
Yes, I guess.
So sorry to take away one information. Maybe you were trying to apply that information, but and you can still think of it that, but actually it is true for any quadrilateral. I actually made a calculation mistake. I thought that it was some special quadrilateral. So for any quadrilateral, if you draw squares like this, then the centers of those opposite sides will be. So don't, if you already drawn the diagram, don't erase it because of course it is true for a quadrilateral which has this property. Don't rely on that. So sorry to destroy the work that you may already done. Complex number 6. Yes, correct. Yeah, very simple. And it is true for any quadrilateral, right? So can you answer the question? Neither. I was thinking that if this is true, then this is true. So I was going to ask, is the converse true? But the काय तेच नाही तर काय संबंधच नाही कॉन्व्हर्सचा. अशाच प्रकारे ट्रायंगलच्या दोन्ही साईडवर जे आपण स्क्वेअर काढतो तर त्याच्या सेंटरमध्ये पण काहीतरी रिलेशन असतं ना.
येस सर, लाईक जे सोल्युशन माझ्याकडे आहे त्यामध्ये पहिल्यांदा आपण त्याची प्रॉपर्टी प्रूव्ह करतो आणि मग ती
हा.
ह्यात apply
अच्छा, ती प्रॉपर्टी काय एक्झॅक्टली मला तर आठवत नाही.
करतो. मिड पॉइंट कन्सिडर करतो साइडचा अँड सेंटर अँड मिड पॉइंट मध्ये आपल्याला आयसोसेलेस राईट अँगल.
हा करेक्ट. तिसरी साईडचा मिड पॉईंट आणि ह्याचा तो 45 नाही करेक्ट करेक्ट. Yeah. So for others reference, what we are saying is that there is a very similar property when, just correct me if this is the right one, that in any triangle, if you construct squares on the two sides, and if you take the centers of those squares, that those two centers and the midpoint of the third side, they become a 45-45-90 triangle always. That is a property, and that what Om is saying that you can use this to solve the given problem in pure geometry. Okay, but anyway, so let me show the complex numbers way of doing this question. So I'll just denote, I will not draw the squares because I'm only interested in the centers, right? Okay. So as usual, we always denote the complex coordinate with the small letter, right? So the complex coordinate of ABCD can be denoted as small a, small b, small c, and small d. Right. So now the first question is, can we describe the points PQRS in terms of ABCD? Because we know the relation, right? We know that this is forming a 45-40-90 triangle. So in terms of all the transformations you have studied, if I call the coordinate of this small p, then small p as a complex number can be written as what? So always it is good to think of this like a recipe, like a series of steps you have to take to reach the point P. To reach the point P, you can first arrive at the point A, right? So I start with the point A. And from the point A, I need to go to this distance AP, right? So I need to go to P minus A. But what is P minus A itself? If you know this is a 45-45-90 triangle, can we relate the P minus A with B minus A? Like if you just think of them as vectors for a minute, that this is one vector and this is another vector. So you see there is a spiral homothety happening there. The same thing which we applied earlier, that with a suitable angle and ratio, this first vector can become the second vector. So if you just look at that, so this can also be written as B minus A times. So it's a rotation of 45 degrees and reduction of 1 by root 2, right? So I can write it as 1 by root 2, 645 degrees. Right? And like every time writing this symbol again and again can become tiresome. So I can simplify, and because this constant will keep appearing again and again. So I can call this alpha temporarily. Okay, because the same alpha is going to occur on all the four sides. Right. So if I just call this as alpha, then just going to say that my point P is A plus B minus A times alpha. Right. Okay, so I hope this kind of recipe approach is clear, that you first reach A, then from A you pick the direction based on some spiral homothety. And if you follow the same recipe for all the other points, right? Same thing to reach Q. And now as I write it in your mind, the recipe should play out. So to reach Q, I have to reach point B. And from point B, I have to take the vector BC. And to that, I have to do the appropriate rotation and scaling. And same for R and S, right? Like cyclically, you can just write the expression. So we obtained the coordinates of points PQRS very quickly. Okay. And now what we are interested in the segment PR and QS, right? So I am interested in segment PR, or if I say that as vector PR, so which is vector R minus P, right? This this is the arrow which I'm interested in, because that is the one line segment, and the other is going from Q to S. So I would like to obtain the expressions for these two vectors, right? And always if you want to find a vector or expression, it is the end minus the start, right? The tip of the vector minus the head of what is called the tip, what is called the head, anyway. But basically the ending point of the arrow minus the starting point of the arrow. So therefore this can be written as C minus A plus and QS can be written in the same way as S minus Q. Okay, and we can in this, if you see here, that the term C minus A is coming here also, and inside the bracket also there is a C minus A, and it's D minus B is also like that. So actually you can rearrange the whole equation in terms of C minus A and D minus B as the repeating blocks. So I can just give them some special names. I don't want to keep writing in them every time. So we can say let C minus A be denoted by X and D minus B be denoted by Y. And you see, I'm choosing them as X and Y because they are like the independent variables that I can freely choose X and Y anyhow I want, and everything else will be described in terms of that, right? So therefore, in this way, the first term R minus P can be written as X minus alpha X and D minus B plus alpha. Or in other words, I can take alpha X common. Okay, so R minus P becomes X times 1 minus alpha plus Y times alpha. And the second one becomes Y. And now you see the sign is reversed because here it is minus C plus A. So it has to be minus X. Okay. And all along we know what is the value of alpha. So by the way, this is the expression of alpha in what we call polar coordinates, but we can also write it in normal XY coordinates, because again, remember that one rule, that whatever that transformation does to any point in the plane, it also does to the unit point, that 1 comma 0. So I can quickly obtain the value of that alpha, like if I just draw it here, right? Because in this diagram, what I know is that alpha is the operation that took my AB to AP, right? So on the side, if I just draw a small coordinate system, right? And in that, so this is my origin, this is my unit point. And just imagine that if I do that same operation to the unit point, where am I going to go? So if I do the same rotation and dilation, like if I form the same shape 45, 45, 90 triangle, what is the coordinate of this point? That is my alpha, right? So how much is that? You see it is half plus half I. Both x and y coordinate are half, 0.5, right? So and the same point which we are calling alpha, which in a polar form is 1 by root 2 angle 45 degrees, can also be written as simply half plus half I. Okay. So if you want to substitute the value at any point, we just put half plus half I. Okay. So we got the PR and QS vectors like this. And so at this point, all we have to do to prove that they are equal and perpendicular is that if I rotate one segment by 90 degrees, it should become the other segment, right? And again, that is where the transformation has given that what is the meaning of rotation by 90 degrees? It is multiplication by cis 90 degrees. Cos 90 plus I sin 90. But how much is cos 90 plus I sin 90? It is simply I, right? So again, in the coordinate system, if you think about it, rotating this point by 90 degrees will take me from here to here. And this point is nothing but 0, 1, or which is 0 plus 1 I, which is I. So therefore, rotating by 90 degrees same as multiplication by I. So if the property is true, and in my diagram I need to check the corresponding that which vector will be rotated into which one anti-clockwise. So QS rotated anti-clockwise will become PR, right? So what I expect is that QS, or that is S minus Q, rotated by 90 degrees should equal PR. So if this relation is true, then we have proved what we want. The first vector S minus Q rotated by multiplied by I, which is the same as rotation by 90 degrees, should become the second one. So now it's just a algebraic calculation, right? We just need to multiply, literally multiply and check. So if I write S minus Q times I is what S minus Q is given over here. So Y times 1 minus alpha times I minus X times alpha times. So let us see what happens. So what is the, and I already know what is alpha, right? Alpha was half plus half, right? So what is 1 minus alpha? Half minus. So I can substitute both alpha and 1 minus alpha in that equation, and let us see what happens. So if I multiply I inside the bracket, so this will become half I, and minus I into I will become I square, which will cancel with the minus sign. So you'll get simply half I plus half minus X times, here again you'll get half I square minus. And so I need to compare this equation with PR. What is PR? This one, right? So if it is the same equation, we are done. So if you look at it here, what I expect as the coefficient of y, the coefficient of y should be alpha, right? So is this the same as alpha? Yes, right? And what do I expect the coefficient of x as 1 minus alpha? So is the coefficient of x 1 minus alpha? Yes. I'll just take the plus sign inside. So this is correct, right? So this is alpha and this is 1 minus alpha. So it is working as expected. And what I earlier thought that x and y have to be perpendicular, that is not required. Okay. So I don't know, some of you are already seeing these calculations second or third time, but those who are seeing it for the first time, just take a moment to appreciate that how every step is working out and how we are going back and forth between algebra and geometry. That in our mind, I'm rotating a vector, but while writing on paper and multiplying by I. So that sort of mind-body coordination or geometry algebra coordination has to become established. That while writing the algebra in the mind, you're doing the geometry. And the sort of the way to get familiar with this is through geometric transformations. Okay. So there is a book by I.M. Yaglom, so who is the same author of the geometric transformation series called Complex Numbers in Geometry. Does anybody know this book already? This is a very amazing book. So same author, I.M. Yaglom. Okay, I think you can find this book easily in without copyright also. I think it is complex numbers. I forget it is either in geometry or and geometry. But this is a really amazing book because it gives you all sorts of more useful properties that so far we already seen very basic things that what is a rotation, what is a dilation. He will give you conditions under which 4 points are cyclic. So if 4 points are cyclic, what is the condition in terms of their complex coordinates? Or if you know the three vertices of a triangle, can you describe the complex equation of this circumcircle? And so many other things. So, like particularly coming to Olympiad geometry, right? These days we are observing more and more that students prefer to use a tool like complex numbers because, like it or not, the questions are becoming more and more difficult over time. And so sometimes it is like pure geometry is very hard to attempt. So students become experts in this kind of tool like coordinate geometry, complex numbers, and they were the term called bash the problem. Have you heard this term, bashing the problem? Which is that you just apply some brute force technique of doing lots of calculation, and you finish the problem. And so if you want to do the bashing, there are 3-4 options within that also. So one is what is called a trigo bash, where you give some special names alpha, beta, and then in terms of the sine alpha, like apply sine rule, cosine rule to find all the lengths. That is one way. Other is coordinate bashing, where you give coordinates to every point. Then there is a technique called complex bashing, where you use complex coordinates to do the calculation. So I will not recommend one approach or the other. Finally, every person has their own priority. But if you find that you are really liking this complex number stuff, that you are being smart and efficient with it, that it is saving your time, then by all means become a champion of complex numbers and learn to apply them in geometry in a very powerful way. Develop your own lemmas, very important. That if you decide that I want to become an expert in applying complex numbers, don't start working everything from first principles in the exam. You should have your own ready tools available to do small manipulation. Like if I have 2 points and a third point, what is the foot of the perpendicular from that point to this line? Like these small things. What is the equation of angle bisector? What is the equation of perpendicular bisector? All of these should be ready in your toolkit so that you save time in the exam. Otherwise, if each of these mini steps is going to take away your attention, then trying a hard problem with complex numbers will be even that much more challenging. So complex number batching is a very effective technique if applied correctly. And as always, with any calculation based technique, you always have the risk that if you do a mistake, you may lose all marks. Just as if you try to solve a problem with coordinate geometry, getting it half right doesn't really get much value because everybody knows technically every problem can be done with coordinate geometry. In the same way, every problem can be done with complex numbers, but if you are able to do it right till the last step, only then you will get significant credit of that. Okay, so do check out this book. Look at all the possible tools that he is going to give you. And again, look at the first chapter of the book because actually, if you remember when I started talking about complex numbers, I asked you the question that what is so special about the way we define I? Right? We say that x square plus 1 equal to 0 is the equation for which we created this new symbol I. But you may have your own different equation, like somebody likes x square plus 2 equal to 0. And so their I square is not -1, their I square is -2 or something like that. So every person can have their own version of complex numbers. But are these really different complex number or just relabeling? Like just as the same numbers 1, 2, 3 can be referred with a different word in a different language. I can call them ek, don, tin, but it is the same symbols. So the same thing is applicable for complex numbers also. So all of these things you can explore in Yagalom's book to a lot of detail. Okay, we are almost out of time. I'll just leave you with one last question to try, which we'll discuss next time. This is a question from APMO. So APMO is Asia Pacific Maths Olympiad 2010. So I'll just draw the diagram of that. So as usual, H and O is the off center and circumcenter. And so triangle ABC. So M is a point on side AB such that AHCM. So basically, the circumcircle of AHC is intersecting at M, and N is a point on AC. So that the circumcenter of triangle MNH lies on the Euler line. In my diagram, this NH look almost collinear. Okay, but anyway, we don't have time to try this problem today, so we'll discuss it next time. And I think we can probably try this with pure geometry also. But if you just Google like complex numbers in geometry, you'll get lots of resources online also. But you see how many problems are around orthogonal configuration. Like even in INMO training camp, we were seeing that there are so many questions that revolve around orthogonal configuration. Seems like there is almost endless supply of possibilities in that ortho center. Okay, that's all for now then. Thank you. We'll meet next time.
Bye, sir.
Thank you, sir.
Bye, sir.